Welcome to lecture on a basic course on electric and magnetic circuits. This lecture on magnetic circuits covers how to solve magnetic coupled circuits problem. We have already discussed in last lecture on the dot convention, the mutual inductance, the voltage developed in the other coil due to the current in first coil and so on. Let us see a circuit like this. So, we have a source this side, we have another source this side. There are two coils L 1 and L 2 having inductances, and R 1 and R 2 are the two resistances in the two circuits. And the inductance L 1 and L 2, the two coils have a mutual inductance M between them, and the dots are provided as already marked here. So, if we write the corresponding equation here, time domain equation here, so we can write down I 1 R 1 plus L 1 d I 1 by dt plus the voltage induced by the coil 2 on coil 1, that is mutual inductance. Why I am writing plus here? Because you see here current I 1 is entering to the dotted terminal and current I 2 also entering to the dotted terminal. I 1 is dotted terminal, I 1 is entering here and I 2 is entering to the dotted terminal. So, therefore, the corresponding mutually induced voltage in L 1 will be positive M, and this will be d I 2 by dt, because the current associated with coil 2 will be coming into the picture in the resulting equation, and this voltage drop equals to the V 1, the input voltage in the system. Similarly, for the I 2, if we write this, then we can write down I 2 R 2 plus the drop in the second inductance L 2. So, this will be L 2 d I 2 by dt, and then again this will be plus M, because current I 2 is entering here and current I 1 is also entering to the dotted terminal, M d I 1 by dt, and the voltage here is the other way, unlike the case of the first coil. So, this will be equals to minus of V 2. So, this is the time domain equation for the two circuits. From the time domain equation, we also learn how to write the corresponding frequency domain equation. We have studied in the AC circuits like in the form of impedance and so. So, that leads to a situation, after writing the time domain equation, we can take the corresponding frequency domain equation, that becomes equals to R 1 I 1 phasor j omega L 1 I 1 plus j omega M I 2 equals to V 1. See here I 1 R 1 L 1 d I 1 by dt M d I 2 by dt equals to V 1. So, we got the equations to be R 1 I 1 j omega L 1 I 1 plus j omega M I 2 V 1. Only importantly, you see here in the first equation also for the loop 1, the corresponding I 2 term is coming because of the mutual inductance M here. Similarly, for the second equation, time domain equation, the corresponding frequency domain equation becomes omega j omega L 2 I 2 plus j omega M I 1 plus R 2 I 2, that equals to minus of V 2. What you notice here, that the first in the first loop R 1 I 1 associated with I 1, then we are writing the corresponding voltage associated with the inductor L 1 omega L 1 I 1, and it has a mutual component also, voltage developed due to the current I 2, that becomes equals to j omega M I 2. Only we note here that the plus sign here is due to, because at both the dotted end the corresponding I 1 and I 2 are entering. So, we take the corresponding this voltage part to be positive in this case, then comes the source voltage V 1. Similarly, the second loop we talk about first the inductor L 2. So, is of its own drop j omega L 2 I 2 omega L 2 I 2, and the mutual part j omega m I 1, this also comes to be positive the same region as we discussed in the for the first loop, and then the plus R 2 I 2. So, the drop in the R 2 that becomes equals to minus of B 2 here. So, what we say here is that individual component has a drop like here R 1 case and L 1 case for the first loop. So, for the R 1 we have I 1 R 1 and for L 1 we have j omega L 1 I 1 plus the j omega m I 2 the mutual component part. So, L 1 has two components because of the mutual link with the L 2, and that becomes equal to supply voltage V 1. In the second case we have two elements here also R 2 and L 2 where the corresponding voltage drop is associated. So, I 2 into R 2 and in this case I 2 j omega L 2 I 2 plus the corresponding j omega m into the I 1 equals to minus of B 2. So, these are the two equations which you can see for the particular two loops. So, the magnetically coupled circuits between L 1 and L 2 the coupling happens to be there. We can write the individual equation as the frequency domain equation in terms of the impedance form, we can write like this. So, let us see another case for a circuit like this where we have a voltage source V and we have a current source loop current I 1 here, and in the right hand side we have another loop which is having a current of I 2 in the clockwise, both I 1 and I 2 are in the clockwise direction. First case, a first loop we have a Z 1 impedance and in the second case we have a Z L impedance case. So, let us if you go by the element wise voltage drop we have Z 1. So, this is Z 1 I 1, we have the second element the L 1. L 1 has two components of its own drop, self drop j omega L 1 I 1 and the mutual part. The mutual part if we say I 1 is entering to this dotted terminal and I 2 is leaving to the dotted terminal. So, therefore, this m term becomes negative j omega m and the corresponding current will be I 2 and that equals to the applied voltage V here. For the second loop we see here for the ZL element, the ZL element has a drop of ZL I 2 and then the next element second element in the second loop that has a j omega L 2 I 2 self and the mutual part happens to be j omega m I 1 j omega m I 1. Here the corresponding m term happens to be negative because I 2 is leaving and I 1 is entering here. So, the corresponding second equation for the second loop becomes Z L I 2 plus j omega L 2 I 2 minus j omega m I 1 0. So, for this case magnetically coupled circuit case the first step is to write the corresponding loop equations correctly. For that as I said you look into the different element component parts of this loop and for each loop we will have to write the corresponding voltage drop. In case of coupled things we must take into account the corresponding mutual component. For mutual component it is not the current of the associated circuit, it is the current of the coupled circuit. So, we will proceed for few more problems to discuss in this lecture. So, that you can comfortably write different equations for different such coupled circuits problem. So, let us have a circuit like this which has a source 50 volt source, 2 ohm resistance and capacitance capacitive reactance of minus j 5 and an inductor of j 7 ohm and another inductor with a coupled thing having j 9 ohm and then a fourth one is having a resistance of 4 ohm. Now, in this case we have two loops I 1 having a currents of I 1 and I 2 clockwise as shown. Now, we need to write the corresponding as learned from the earlier study about the two loop equations for the two loops loop 1 and loop 2. So, loop 1 has a first element the resistance. So, this has a drop of 2 into I 1 and then the second element has a minus j 5 into I 1 straightforward. Then we have the third element j 7. So, this will be plus j 7 into I 1 and the minus I 2 because the corresponding current here is I 1 minus I 2 downward. in the J7 ohm current flowing is I 1 minus I 2 downward. Such loop equations we have written in case of DC and AC circuits. Now, in addition to this self drop, there will be a mutual drop in the 7 ohm. So, mutual drop will be I 1 minus I 2 downward. So, current is entering here and I 2 is leaving here at this terminal. So, the corresponding mutual term will be negative. So, minus of J of 9, the corresponding current here happens to be I 2 dot. So, for this case 7 ohm inductor here we have the self term first term and we have the mutual term minus J 9, that is the minus J 2 the mutual inductance between this and that. So, J 2 into the I 2 the corresponding current here. So, that becomes equals to the part of the J 7 terms and that becomes equals to your 50 with an angle of 0 degree. This is loop 1. Then we can write similarly for the loop 2 equation. In the loop 2 equation we can have 1, 2, 3 elements. So, we can start with the 4 ohm. So, 4 into I 2 dash I 2 phasor and then we come to the 7 ohm inductor. So, that becomes equals to plus J 7 I 2. It has a mutual component with the 9 ohm. So, therefore, the corresponding, so I 2 is leaving I 2 minus I 1 here, not I 2, because the current I can take the current to be this way or the that way. So, this is I 2 minus I 1 and then this I 2 minus I 1 is leaving to the dotted terminal at this point and I 2 is leaving to the 9 ohm reactor. So, therefore, the corresponding mutual term will be positive J of 2 and that will be I 2, because the current here is I 2. Once again we are considering this element now. In this element I 2 minus I 1 is leaving the dotted terminal and in the coupled with the J 9 ohm the corresponding current I 2 is leaving the dotted terminal. So, therefore, the mutual term will be positive here. So, mutual term is J 2 and the corresponding current in the 9 ohm reactor is I 2. Then we go to the third terminal about the 9 ohm reactor. So, that becomes equals to J 9 into I 2 and it has a coupling with the corresponding J 7 ohm. So, that coupling becomes equals to I 2 is leaving and I 2 minus I 1 is also leaving to the dotted terminal. So, this becomes equals to J plus 2 into I 2 minus I 1. So, this I 2 minus I 1 is the current flowing in the 7 ohm reactor in the upward direction and that is leaving to the dotted terminal, that becomes equals to 0 in this case. So, these are the two equations for the corresponding circuit. So, that is summary of these two equations here, equation 1 and equation 2. 2 I 1 minus J 5 I 1 plus J 7 I 1 minus I 2 minus J 2 I 2, because here current is I 1 minus I 2 is entering to the dotted terminal, I 2 is leaving the J 9 ohm. So, therefore, this becomes equals to minus J 2. In second case it happens to be the, as we started with 4 I 2 J 7 I 2 minus I 1 and plus J 2 I 2 and plus J 9 I 2, this is the mutual part. So, this is combination of the for the J 7 element, J 9 element having like this, the cell part is J 9 I 2 and the mutual part is J 2 I 2 minus I 1, that equals to 0. So, we see here that for the J 7 element we have two components here and here also two components. For J 9 component also we have two components, because J 9 is also having mutually coupled with the J 7. So, write the like this element wise, if we write the corresponding loop equations, then we can reach the correct writing form of the KVL equation for each loop. Now, we can see another example here. So, in this case we have V 1 equals to 10 with an angle of 0 degree. So, let us say in the first loop we have 1 ohm resistance and we have a 10 ohm reactor, and in the second loop we have 400 ohm resistors with a 1000 ohm reactor, and there the 10 ohm and 1000 ohm reactors are having a couple of M equals to J 90 ohm. And then the corresponding we need, the question is that find the phasors across the 400 ohm resistor. So, we need to find the corresponding voltage across the 400 ohm resistor here. That implies that 400 ohm resistors the voltage will be V 2 equals to I 2 into 400. So, we need to solve I 2 to have the corresponding things, you need this is a coupled circuit. So, we need to write the corresponding two loop equations I 1 and I 2 for that, and then you can proceed for the solution for the I 1 and I 2. As already mentioned, we can see the first loop. So, loop 1. So, for loop 1 we have two elements, element 1 ohm resistance and element 2 the inductor. So, we can write down this 1 into I 1 plus the second element the reactor J 10 into I 1, but the second element is a coupled thing. So, now I 1 is entering and I 2 is leaving. So, this leads the corresponding mutual component to be negative minus of J 90 into I 2 dot, and that equals to the corresponding 10 volt here, 10 with an angle of 0. So, that becomes equals to 10 here. So, this is loop 1. Similarly, we can write down the for the loop 2, we can start from the 400. So, 400 into I 2 first element gone, then the second element is having a self 1 J 1000 into I 2 done, and then you can write the corresponding its mutual component. So, I 2 is leaving and I 1 is entering. So, this will be minus J 90 the m part with I 1 dot, and this becomes equals to 0. So, these are the two equations. Using these two equations we can solve the corresponding circuits. So, this loop 1 as I said here 1 I 1 J 10 I 1 minus J 90 I 2. So, this is about the for this second element. Similarly, the loop 2 first element is this, and for the second element we have self and mutual part that equals to 0. So, these are the two equations. Solving the two equations we can find out the I 2 and I 1 value to be as 0.1724 with an angle minus 16.7, and the V 2 value happens to be I 2 into 400. So, that becomes equals to 68.96 angle minus 16.7 degree. Another example, here we have a 5 with an angle 90 volt source, and we have two loops. In the first loop we have only one element J 2 ohm, and the second loop we have another element J 3 ohm, J 3 and J 2 are in the second loop. So, these are the two loops, and then in between then we have a mutual M of J 4 ohm between J 2 and J 3. So, if you see this part, so in the middle branch J 2 ohm, a current flowing I 1 minus I 2, I 1 minus I 2 downward, or you can say I 2 minus I 1 upward, and whereas in the J 3 the corresponding current is only I 2. So, that is the situation here in this case. So, for the loop first loop we can write the equation here. The first loop we have only one element. So, its self voltage is voltage drop is J 2 into I 1 minus I 2, because current flowing through is I 1 minus I 2, and it has a mutual component. I 1 minus I 2 is leaving the dotted terminal and I 2 is entering the dotted terminal. So, this will be a minus m. So, this will be J 4 into I 2, because current flowing in the second one is I 2. So, that this becomes equals to your 5 with an angle of 90 degree. Similarly, you can write for this loop 2. So, loop 2 has two elements. So, you can write for the J 3. So, J of 3 it is a self. So, J 3 of self drop will be this I 2, and then we have a mutual component with the J 3 with this J 2. J 2 has at I 2 it is entering, and then I 2 minus I 1 is also entering to J 2 ohm. I 2 minus I 1 is entering to J 2 ohm. So, then the corresponding mutual part will be positive in that respect. So, the mutual part is J of 4, and this becomes equals to I 2 minus I 1. So, this is I 2 minus I 1. So, this part is nothing but for the J 3 ohm. Now, I will write for the J 2. So, similarly, for J 2 the corresponding voltage drop self drop is J 2 I 2 minus I 1 in the same direction as the I 2 current, that is the corresponding current in J 2, and then of its mutual. So, I 2 minus I 1 is entering the dotted terminal and I 2 is also entering the dotted terminal. So, this corresponding cell becomes equal mutual becomes equals to positive J 4 with I 2. So, that becomes equals to 0 is nothing but for the second loop. So, finally, we got the corresponding equations to be equation 1 and equation 2 to be like this. So, this leads to two equations. So, we got the corresponding I 1 and I 2 to be minus 6.5 and minus 3 ampere respectively. There is another example similar to what we see earlier also. This having 100 volt source in the first loop, having a 4 ohm and minus J 3 ohm and a J 6 ohm reactor, and then in the second loop we have J 8 ohm of reactor which is coupled with the J 6 ohm of reactor, and the dots are provided like this, and we have a 5 ohm resistors in the second loop. Note that the corresponding dotted terminal here is I 1 is entering to the dotted terminal and I 2 is leaving to the dotted terminal. In the J 6 ohm, the current flowing is I 1 minus I 2 downward. So, with that considerations is there, or I 2 minus I 1 upward. So, with that consideration we can take the corresponding plus m value or minus m value, and m here is J 2 ohm. So, for the first loop, in this case loop 1, we can write the equation. We can start from the 4 ohm resistors, 4 into I 1, and then we have the capacitors minus J 3 into I 1, then we have the J 6 ohm. So, for this the corresponding drop associated the self inductance. So, that becomes equals to J 6 into I 1 minus I 2, and then its mutual part. So, this mutual part becomes I 1 minus I 2 is entering and I 2 is leaving. So, this becomes equals to minus of J 2 into I 2, and this equals to 100 volt with 0 degree 100 volt. So, this is about the first loop equation. Then similarly, for the loop 2 equation, we can write down, we can start from the 5. So, 5 into I 2, and then we have the J 6. So, J 6 we can write down plus J 6 I 2 minus I 1 upward, I 2 minus I 1 upward. So, I 2 minus I 1 is upward, is leaving the dotted terminal, and so also the I 2 is leaving the dotted terminal. So, the corresponding mutual inductance becomes positive for this case. So, we are writing the mutual inductance for this. So, that becomes equals to J 2 into I 2 with that respect, and then we go to the J 8 now, plus J 8 I 2. So, that is the drop here, and then I 2, this has a I 2 is leaving, and I 2 minus I 1 in J 6 is leaving. So, therefore, the corresponding drop for this is J 2 with I 2 minus I 1, and that becomes equals to 0. So, we see here for this case J 6 with this part, the one part, and then we have another part for the J 8 part in this case, and that becomes equals to 0. So, we got the corresponding two equations like this. So, the first equation here and the corresponding second equation here for the loop case. So, in the second equation, to reiterate again, 5 I 2 J 6 I 2 minus I 1 plus J 2 I 2, this part both are leaving the corresponding dotted terminal, plus J 8 I 2 plus J 2 I 2 minus I 1 equals to 0, and then the solution for this leads to I 1 equals to 20.3 with an angle of 3.5 degree, and I 2 happens to be 8.693 with 90 degree. This solution for this we can get the way, like you can write down in terms of the, after this simplification of the two equations, and you can write down in terms of the matrix form also this the corresponding matrix in terms of multiplication on I 1 I 2, and then becomes equals to your B 1 B 2 or so. In this case it will be 100 and 0. So, by this way you can use the corresponding matrix form as you have learned in the earlier example, and then from there you can find out the corresponding I 1 and I 2 there also, or you can substitute from the second equation about I 2 equals to in terms of I 1, and then you substitute in equation 1, and you can find out the also I 1 and I 2 respectively. Here in the next example, the question asked is about write the set of 3 loop equations for the circuit. So, there are 3 loops here, loop 1, loop 2 and loop 3. So, in the first loop, if we see there is a 5 ohm resistance and it has a 7 ohm reactance. So, this 7 ohm reactance is having coupled with the 6 ohm reactance. How they are coupled? So, coupled in 7 ohm resistance, the corresponding current is I 1 minus I 2 downward or I 2 minus I 1 upward. In the 6 ohm resistance reactance, the corresponding current is I 2 minus I 3 downward or I 3 minus I 2 upward. So, this is in the 6 ohm reactance and this is in the 7 ohm reactance. So, with that consideration of the current the two branches of these reactors, we need to write the corresponding coupled equation. Like for the loop 1, we can write in the 5 ohm resistance the corresponding drop will be 5 I 1. Then we come to the 7 ohm of itself, this will be J 7 I 1 minus I 2, the downward current, and the mutual part will write. So, I 1 minus I 2 is entering to the dotted terminal, and here I 2 minus I 1 is leaving to the dotted terminal. So, this becomes negative. So, the negative is mutual part is J 2. So, minus of J 2 and the corresponding current in the coupled circuit is I 2 minus I 3 downward, I 3 minus I 3 downward. So, this is the corresponding drop part in case of associated the J 7, and then this becomes equals to your V 1 phasor. So, this is loop 1. Similarly, we can write for the loop 2 also. For loop 2, we see here there are 3 elements 1, 2 and 3. So, we can start with the capacitor 1 by J I 2, and then we have the this second element J 6, I 2 minus I 3 downward, I 2 minus I 3 downward, and then it has a mutual component with this. So, this has downward it is leaving, and I 2 minus I 1 is also leaving to this dotted terminal. Once again I 2 minus I 1 is also leaving to the dotted terminal in J 7. So, I wrote the corresponding J 2 J I 2 minus I 1, or otherwise you can write down I 1 minus I 2 downward means the corresponding it will be minus 2 J, it will come out to be same. So, I am writing I 2 minus I 1 going upward, and that current is leaving the dotted terminal, and here in this case I 2 minus I 3 is leaving the dotted terminal. So, therefore, the corresponding mutual components happens to be plus 2 J. So, this is about the 6 ohm part. Now, you come to the 7 ohm part. In 7 ohm I 2 minus I 1 is upward. So, that is a self, and then the mutual part I 2 minus I 1 is upward dotted terminal leaving, and along with the I 2 minus I 3 dotted terminal leaving. So, the mutual part happens to be positive 2 J I 2 minus I 3, that equals to 0. So, this is the second equation. Third equation, we can start from the 3. So, 3 I 3, and then we can write the corresponding the J 6 part. So, this will be 6 J I 3 minus I 2 in the same direction as I 3, I can write, that becomes easier I 3 minus I 2, and then I 3 minus I 2 is entering the dotted terminal, and to this coupled circuit the corresponding I 2 minus I 1 is leaving the dotted terminal, I 2 minus I 1 is leaving the dotted terminal. So, this 2 becomes mutual component becomes negative minus 2 J I 2 minus I 1, and that becomes equals to 0. So, this is about the equation 3. So, we got the corresponding 3 equations, and from there we can find the solution for the network also. There are different kinds of questions can be asked in this coupled circuit also. So, this is a question for this coupled circuit which has a voltage source V 1 and V 2 in the 2 loops. In the first loop we have 5 ohm and J 8 ohm, and in the second loop we have 2 ohm and J 2 ohm, and J 8 and J 2 the corresponding reactors are having a coupled things, I 1 entering to the dotted terminal and I 2 leaving to the dotted terminal. If we consider that way, the mutual inductance becomes negative in that case. So, the question asks is that find the ratio of V 2 upon V 1 phasors resulting in 0 current I 1. So, that the I 1 becomes equals to 0. So, what should be the corresponding ratio of V 2 and V 1? So, the corresponding I 1 becomes 0. So, we will write the corresponding 2 loop equations, loop 1 and loop 2, and then from there we will put the corresponding I 1 value to be 0 and find the corresponding V 1 value relation. So, for loop 1 equation, as we have discussed earlier, the first element is 5 ohm. So, current flowing is 5 into I 1, the second line is J 8. So, it is a cell part. So, we had J 8 with the current flowing is I 1 done. It has a mutual component and the mutual component I 1 is entering, I 2 is leaving. So, therefore, it has a mutual component negative. The mutual component is J 2 and J 2 and the corresponding current is I 2 dot. So, this becomes equals to your V 1. So, that is done. The next one is for the loop 2. So, loop 2 we have a similar J 2 ohm and 2 ohm this. So, in this case I can start with the J 2. So, J 2 cell will be I 2 and then J 2 has a mutual component. So, the mutual component I 2 is I 2 is leaving and I 1 is entering. So, that will result in minus of J 2 the mutual part into I 1 and then in the 2 ohm it will be 2 with an of I 2 and that equals to minus of P 1 B 2. So, these are the two relations for this. So, we got the equation 1 and equation 2 and in this case we can substitute this I 1 to be equals to 0 and then we can get the simplified things from there. So, as I said here we got the loop equation 1 and loop equation 2 and substitute I 1 equals to 0. So, that leaves the corresponding I 1 to be equals to 0 means in the first equation we got minus J 2 I 2 equals to V 1 and the second equation substituting I 1 to be 0 equals to we got minus 2 plus J 2 I 2 equals to V 2. So, V 1 V 2 upon V 1 ratio that becomes equals to this ratio and that becomes equals to 1 minus J. So, the conclusion is that if the V 2 by V 1 ratio happens to be 1 minus J, then the corresponding current happens to be a corresponding current I 1 happens to be equals to 0. So, that is why we solve the corresponding problem in terms of this. We have another example on the coupled circuit. Now, let us see this example. We have a source of 50 with an angle of 45 degree and we have 3 ohm, 4 ohm reactor, J 5 ohm reactor and we have minus J 8 ohm capacitor part. But you note here that J 4 ohm and J 5 ohm reactors they have a couple and the mutual reactance between them is J 3 ohm. Now, the dots are provided. So, if you see this circuit there are two loops for I 1 and I 2 as seen. The current in the middle branch in the J 5 ohm is having a current I 1 minus I 2 downward. So, that you have to notice or I 2 minus I 1 upward. Now, when you consider I 1 minus I 2 downward, note that it goes to the dotted terminal, enters the dotted terminal I 1 minus I 2 for J 5 and in the first inductor J 4 ohm that the corresponding I 1 enters to this one. So, if you consider the current in inductor J 4 ohm I 1 and current in J 5 ohm I 1 minus I 2, then in both the inductors currents are entering to the dotted terminal. So, the mutual reactance J 3 will be positive. Okay. So, that considerations will proceed for the corresponding two loop equations and go by that. So, let us say first loop 1 the corresponding equations will be we have 3 elements here 3 ohm, 4 ohm and the 5 ohm. So, write for the 3 ohm first. So, this becomes equals to 3 into I 1 plus J 4 into I 1. Now, we will go to the mutual part of the J 4. So, that becomes equals to that the corresponding current in the J 5 will be I 1 minus I 2 downward. So, therefore, that will result in positive M. So, J 3 into I 1 minus I 2. So, that is about the for the 4 ohm. Next we will go for the J 5. So, that becomes equals to J 5 with I 1 minus I 2 downward and its mutual with J 4 that will be equals to plus J 3 into I 1 and this becomes equals to your 50 with an angle of 45 degree. So, we see here this part is for the J 4 ohm and this part is for the J 5 ohm reactor. Similarly, we can write for this loop 2. So, in the loop 2 we will write the corresponding equation. We can start from this minus J 8 and this becomes equals to the corresponding current is I 2, this is I 2, and then we will go for this J 5 second element only. So, this become equals to plus J 5 into I 2 minus I 1 upward. So, with this the corresponding mutual becomes equals to, for its mutual component becomes equals to, because I 2 minus I 1 is upward and it is leaving the dotted terminal, but I 1 is entering the dotted terminal. So, the corresponding mutual part becomes negative J of 3 into I 1. So, these are the two elements. So, two drops are added here. So, this is for the J 5 part and this for the capacitor part. So, this becomes equals to 0. With this we can write the corresponding two equations, and then we need to find the corresponding voltage drop across the 5 ohm. Note that voltage across the 5 ohm we can find out two ways. One is the drop across the minus J 8 ohm. So, for that drop across the minus 5 ohm, this is, let us say V J 5, this becomes equals to V minus J 8. So, V minus J 8 equals to I 2 into the corresponding reactance minus J 8. So, this is one way. Otherwise, we will find the corresponding voltage drop across here. So, the voltage across J 5 equals to, we say here I 1 minus I 2 downward, that current is flowing downward, and this into the corresponding J 5 what we did here plus J 3 I 1. So, this will be the corresponding drop for the corresponding across the J 5. So, that way also you can find out and find the things. So, this results in that for the loop 1 we find the corresponding 3 I 1, and then we have the corresponding voltage drop in the 4 ohm, that is J 4 I 1, 3 J 1 I 1 minus I 2, and then we have J 5 I 1 minus I 2 plus J 3 I 1, and that equals to 50 with an angle of 45 degree. So, this gives us the loop 1 equations, that becomes equals to 3 plus J 15 I 1 minus J 8 I 2 equals to 50 with an angle of 45 degree. Similarly, for loop 2 also we write the equations. So, this becomes equals to this corresponding equation becomes this, and then this gives us 2 to be J 8 I 1 plus J 3 I 2 equals to 0, and this gives us the I 1 to be 1.37 minus 40.28 and I 2 to be 3.66 minus 139.72. So, V 5 becomes equals to as mentioned here, the across this becomes equals to J 5 I 1 minus I 2 plus J 3 I 1 or equals to I 2 into minus J 8, and that gives us the corresponding voltage to be 29.27 49.72 volt. So, this is another example on coupled circuit. Another example, different types. So, find the impedance seen by the supply with voltage V 1. So, this is the supply side, which has a frequency of angular frequency of omega equals to 1 radian per second, and the circuit is like that. So, one inductor here and one another inductor here, and both are having coupled as shown here, and the marked currents are I 1 and I 2 like this. So, I 1 is entering to the dotted terminal, I 2 also entering to the dotted terminal. The question asks the find the impedance as seen by the voltage supply V 1. So, the other way we can find out the corresponding Z 1 seen by the voltage supply V 1, that becomes equals to V 1 upon I 1. So, this V 1 upon I 1 can be found out, and by solving the corresponding network. So, if we the expression for I 1 and I 2 should be in terms of V 1 should be obtained. So, once you know the corresponding I 1 in terms of V 1, we can find out for the V 1 aspect. So, in the first loop, this is the first loop I 1. So, the corresponding components are 1 Henry and the 2 ohm. So, for the 1 Henry case loop 1, we can write down the corresponding voltage drop equation. So, this will be 1 radian. So, the corresponding drop the corresponding impedance reactance happens to be also 1. So, this will be 1 into I 1, this is the cell part, and the mutual part current entering I 1 is positive entering to the dotted terminal, I 2 also entering dotted terminal. So, this will be plus. So, the mutual is 1 by 3. So, this will be J 1 by 3 and this will be J 1 sorry. and then J 1 by 3 and then the corresponding I 2 here, I 2 dot here. So, this is the self and mutual part is over for the first element, and then we have this 2 ohm case. For this case, this will be 2 resistance and the corresponding current through them is I 1 plus I 2. So, this becomes equals to 0 for the first case, equals to V 1 for the first case, first loop, loop 1. Similarly, you can write down for the loop 2, and we got the loop 1 equation and we got the corresponding loop 2 equation like this also. In loop 2 equations, we have 3 elements, first, second and third. So, we have J 1 2 element independent of anything. So, this will be I 2, and then we have the J by 4 I 2, we are going by this. So, current is flowing like this, and then we have the J 4 I 2 self, and then it has a mutual component of this. So, this is I 2 is entering to the dotted terminal, I 1 is also entering. So, this becomes a positive M, J 1 by 3 I 1, and the corresponding drop here I 1, this becomes also I 1 plus I 2, that becomes equals to 0. So, we got the 2 equation loop 1 and loop 2, and from there we can this loop 2 becomes equals to I 1 plus I 2 equals to 0, and so therefore, we can substitute I 2 equals to minus I 1 there and in the first equation, and then we got the Z 1 to be equals to V 1 upon I 1, and that becomes equals to J 2 upon 3 ohm. So, the seen impedance from the source side will be the J 2 by 3 ohm. So, in general we saw several magnetically coupled circuit problems and how to solve them. In the coupled circuits, we saw that for each element resistance or inductance, each element the corresponding drop has to be accounted, and we can write the corresponding loop equations for that in a systematic way. After writing the loop equations, we can find out the corresponding loop currents by solution either a matrix approach or the substitution approach, and from there you can find out different things, like you can find the different voltage drops, you can find the corresponding reactive power contributed by the source, or we can find the corresponding complex power associated with the different sources, and so.